Hi, my name is Ray Lee, and I'll be talking about coded trace reconstruction in a constant number of traces. This is joint work with Joshua Brackenseek and Bruce Spang. I'll start with an outline of the talk. You'll see the slide again at the end. We'll start by motivating our problem of coded trace reconstruction by DNA storage. Then I'll formally introduce the trace reconstruction problem and tell you a little bit about what's known. It's a difficult problem. Then I'll tell you about our results. First, we can do coded trace reconstruction in a constant number of traces. I'll show this result from a coding theory perspective and a trace reconstruction perspective. I'll then talk about our second result, which is an equivalence between coded trace reconstruction and average case tree construction. And then I'll tell you about some results we get for trace reconstruction over larger alphabets, and I'll sketch the proof. So our problem of coded trace reconstruction is motivated by DNA storage. DNA storage is a new candidate for archival data storage, and it has advantages over existing technologies like flash memory. But there are some challenges associated with developing good DNA storage technology, and our work addresses one of these challenges. So here's a very simplified picture of DNA storage. You have some data and you write it to some DNA. We'll ignore the fact that DNA has alphabet size 4, and we'll just assume everything's binary. That's not the primary difficulty of the problem. And then, so we can write our DNA, and we can also read our DNA. There's a few ways to do this. One of the primary ways is something called nanopore sequencing. And sweeping a lot of details under the rug, nanopore sequencing produces some noisy copies of our data, which we call traces. And from the traces, we can recover our data. And this talk is going to be concerned with this last step of recovering our data from the traces. And we'll deal with a particular formulation of this problem called trace reconstruction. So before we continue, I'll give a disclaimer that all of our results are theoretical. The constants can be pretty large. And so, but we hope that the ideas that we use could be valuable in practice. So here's our picture again. And the question we're concerned with is how much does coding help with trace reconstruction? So now, instead of writing our data directly to DNA, we might add some redundancy to our data to get a slightly longer string, which we call a code word. Then we write the code word to the DNA. And when we read the DNA, we get noisy copies of our code word. From these traces, we then try to recover the code word and therefore the data. The question is how much does adding redundancy help with trace reconstruction? And we're going to see that it helps quite a bit. So now I'll define everything for you formally. So what is a code? A code is not a Python program. In this talk, a code is simply a set of strings of some fixed length over some fixed alphabet. And here C, we say, is a binary code of length n. Elements of C are called code words. And the crucial parameter for a code is something called the rate. It's given by this definition, always a number between 0 and 1. It's a measure of how good the code is, how big the code is, how non-redundant it is, and the larger the rate, the better. In this talk, we'll be concerned with codes of high rate, so that's rate 1 minus epsilon. And so what does that mean? Well, you plug it into the definition, that means you can think of this as your code has size 2 to the n times 1 minus epsilon. You can also think of this as your code words have epsilon n redundant bits. So that means that 1 minus epsilon fraction of the bits tell you what your code word is, and the other epsilon n are extra. And lastly, you can think of this as there's a bijection between length n times 1 minus epsilon strings and your code. And this bijection is often called the encoding function. And this encoding function is exactly the encoding step where we added redundancy to our data in the previous slide. You can also define codes over larger alphabets, and there's an analogous definition of the rate, and we'll see this later in the talk. I told you what a code is, now I'll tell you about trace reconstruction. The primary object for trace reconstruction is the binary deletion channel. It takes as input a string and outputs another string where each bit or symbol is deleted independently with the same probability q. Crucially, these are deletions and not erasures, so we do not know the positions of the deletions, and so we get a shorter string. The fact that we don't know the position of the deletions makes this a particularly difficult object to analyze. So the trace reconstruction problem says there's an unknown string of some length n, and you're given several independent outputs of this trace through the binary deletion channel. And you want to recover the unknown string given the traces. And typically this problem is formulated as how many traces do you need so that you can recover with some reasonable probability, like 2/3. Now, if you're trying to formulate this problem yourself, you probably come up with something called worst case reconstruction. In this case, you know nothing about the unknown string, and you need to recover with probably at least 2/3 no matter what the string is. You can also think of this as that there's an adversary that looks at your reconstruction algorithm and picks the worst case string, and you need to recover with probably at least 2/3 in that case. There's also average case reconstruction where your unknown string is known to be uniformly random from 0, 1 to the n, and then you need to recover with probability 2/3 over the randomness of the traces and the randomness of the unknown string. In this talk, we'll be concerned with coded trace reconstruction, where you get to design a code of rate 1 minus epsilon such that you can do trace reconstruction when the unknown string is from your code. And notice this corresponds exactly to that picture we showed where you're encoding the code words into DNA and then you're getting traces of the code words and need to recover the code word from the traces. So now that we've defined trace reconstruction, I can tell you what's known about worst case and average case trace reconstruction. For worst case reconstruction, there's an easy algorithm, which is you wait until you get a string with no deletions, and then you know your unknown string. Less trivially, the best known upper bound until very recently was that you could do it in 2 to the cube root of n traces. And this works for any deletion probability q. Very recently, it was posted on the archive that you could do trace reconstruction into the 5th root of n traces if your deletion probability is at most a half. So these two results give the state of the art. And the best lower bound is only a polynomial in n, so n to the 3/2. And so you can see there's an exponential gap between the best upper and lower bounds for trace reconstruction. For average case reconstruction, you can do better than worst case reconstruction. You can do trace reconstruction in subpolynomial in n many traces, 2 to the cube root log n. And then there's a lower bound of log to the 5/2 n, so polylogarithmic in n. And you can see again, for average case, there's an exponential gap between the best upper and lower bounds. So as you can see, this is a difficult problem. Typically, trace reconstruction is defined over the deletion channel, but you could just as easily define it over other channels like the erasure channel where you know the positions of the erasures. And in this case, the problem is much easier. Both the problem is easier in that it takes fewer traces, and it's also easier for us to analyze. So it's an easy exercise to show that for the erasure channel, trace reconstruction needs log n traces, and it's possible, so that's optimal. So now I can tell you about our results. So here's the best upper and lower bounds for worst and average case reconstruction. And at the beginning of the talk, we asked, how much does coding help with trace reconstruction? And we'll see here that it helps quite a bit. So we show that there exist codes of rate 1 minus epsilon that can be decoded from 2 to the cube root log 1 over epsilon traces. And we also show a lower bound saying log to the 5/2 1 over epsilon traces roughly are necessary. So from worst case reconstruction to coded trace reconstruction, we go from an exponential upper bound to a constant upper bound. So a couple of things to note. As I said, we do this in a constant number of traces. Asymptotically, it's a good constant. It's subpolynomial 1 over epsilon. Both our upper and lower bounds work for any constant deletion probability q. We also get polynomial time encoding and decoding for constant epsilon. Polynomial time encoding means that the encoding function I told you about earlier, the bijection, can be computed in polynomial time. And decoding means you can recover the unknown string, the code word from the traces in polynomial time. Lastly, when the coded trace reconstruction problem was first formulated, some constructions were given when epsilon was going to 0 with n. And our construction, our upper bound, also works when epsilon is going to 0 with n. And in these parameter regimes, we improve over the number of traces. There's an asterisk because when epsilon is 1 over log n, the previous construction had polynomial time encoding and decoding, while in this setting, we only have polynomial time decoding. So our upper and lower bounds for coded trace reconstruction may look suspiciously similar to the upper and lower bounds for average case reconstruction. And this is no coincidence because they follow from a pair of black box results. So let T of n be the optimal number of traces for average case reconstruction on length n strings. And we prove the following pair of results. First, there exists rate 1 minus epsilon codes using T of roughly 1 over epsilon traces. And all codes of rate 1 minus epsilon need T of square root 1 over epsilon traces. So now we can just plug in directly the upper and lower bounds for average case reconstruction into these blue results to get our upper and lower bounds that you saw in the previous slide. Furthermore, what this tells us is that any improvement to average case trace reconstruction gives an improvement to rate 1 minus epsilon coded trace reconstruction. So if you get a better upper bound, for example, you can just plug it into the blue result and get a better upper bound for coded trace reconstruction. Furthermore, notice that both upper and lower bounds involved t of polynomial 1 over epsilon. And because there's logs everywhere, the polynomial just gets thrown into a constant. And so the reverse direction also holds. So any improvement to rate 1 minus epsilon coded trace reconstruction will give you an improvement to average case trace reconstruction. The any is in quotes and the arrow is a squiggly because there's a polylog factor in our upper bound, and so this is vice versa holds up to polylog factors. Another way you can think about our results is that our results are basically the best possible given our knowledge of average case trace reconstruction. If you were to get any improvement to coded trace reconstruction, either in the upper or lower bound that's substantial, then that would imply a corresponding improvement to the best upper and lower bounds for average case trace reconstruction. So I've told you our results from the trace reconstruction perspective, both that coding does help for trace reconstruction and that average case reconstruction and coded trace reconstruction, there's this equivalence between them. Now I'll tell you our results from a coding theory perspective. So we could ask, can you do trace reconstruction with just one trace? Clearly, you can't do worst case reconstruction, but could you do coded trace reconstruction? So if you have one trace, what's the largest rate of a code you can get such that you can decode from one trace? In information theory language, this is exactly the question of what is the capacity of the binary deletion channel. And this is a well-studied problem. It's a difficult problem. And in this picture, I sketched the best known results, I think. And as you can see, there's a lot of different works and there's some gaps to close. So we have that one trace reconstruction, the capacity of the binary deletion channel. You could ask if you have 2 traces or 3 traces or a constant number of traces, what's the resulting capacity of the channel? And this has actually been studied before. It's been shown that if your deletion probability is going to 0, then we can pin down exactly the capacity of the channel when there's a constant number of traces. So it's something like 1 minus binary entropy of q to the t, where t is the number of traces. If there were 2 traces or 3 traces, we know capacity when q is going to 0, but we don't know the capacity when q is a constant like 1/2. And what our results show is we can handle any constant deletion probability when we have enough traces. So for arbitrary q between 0 and 1 and arbitrary rate, we can achieve that rate with that deletion probability if we have enough traces. So now I'll tell you about our last pair of results, which handles trace reconstruction over larger alphabets. So you can define the trace reconstruction problem over any alphabet. And in this setting, we show that there exists rate 1 minus epsilon codes using log 1 over epsilon traces if your alphabet is a sufficiently large constant. And furthermore, we show that this is tight, that log 1 over epsilon traces are necessary. So a couple of things to note is that we even get the correct dependence on q in the number of traces. And our upper bound is log 1 over epsilon, which is strictly better than the binary lower bound of log to the 5 halves 1 over epsilon. So large alphabet coded trace reconstruction is strictly easier than binary coded trace reconstruction. And lastly, as far as we know, this is one of the few type trace reconstruction results for the deletion channel. So in the remainder of the talk, I'll sketch the ideas and the proofs of these results, and I'll focus on the large alphabet results. So we'll start with the easiest result, which is the large alphabet lower bound that any rate 1 minus epsilon code needs log 1 over epsilon traces. So to prove a lower bound for the deletion channel, it suffices to prove a lower bound for trace reconstruction over the strictly easier erasure channel because we know the positions of the erasures. So a classical result of Shannon says that any rate 1 minus epsilon code can tolerate at most epsilon fraction of random erasures. But in the erasure channel, if we're receiving t traces, each with erasure probability q, that's basically the same as receiving 1 trace with erasure probability q to the t, because the only time we don't know a symbol is if it's erased in every trace. So now we just need the erasure probability q to the t to be at most epsilon which means that t needs to be at least log 1 over epsilon. So therefore, you need at least log 1 over epsilon traces, and therefore you need at least log 1 over epsilon traces for the deletion channel. So in Shannon's classic paper, he also shows that there exist codes of rate 1 minus epsilon tolerating epsilon fraction of erasures, and that implies that log 1 over epsilon traces suffices for erasure channel trace reconstruction. And on the next slide, we're sort of going to use this idea to show that log 1 over epsilon traces suffices for the deletion channel. So now we'll turn to our large alphabet upper bound. So we show that there exists rate 1 minus epsilon codes over a sufficiently large constant alphabet that use log 1 over epsilon traces. So the basic idea is to turn deletions into erasures somehow. So let's start with a code that tolerates epsilon and erasures. And let's cheat. Let's attach to each CI the index I, and we'll fix this problem later. So now our code word looks like the one shown, where the symbols are a combination of code word symbol and an index. So now when you send this through the deletion channel, you get a bunch of traces, and for each symbol in each trace, you know exactly which symbol it came from because it's got its index attached to it. And then you can just align the traces and figure out what each of the symbols are. And the only time you don't know a symbol is when it got deleted in every trace. And in that case, you just use the fact that C tolerates some erasures to correct those erasures. So here, this is basically the same thing that happens in the erasure channel trace reconstruction. And so we've basically turned QN deletions into QN erasures and we can do this in log 1 over epsilon traces. The obvious problem with this is that we attach these indices to these code words and the rate is going to be very small. So how are we going to get around this? We're going to use something called synchronization strings. These were introduced by Horkler and Shirasby in this beautiful paper. And if you've read their original paper on insertion and deletion codes, we'd use the exact same construction, but analyze it for a trace reconstruction. So you fix this thing called a synchronization string S1 to Sn. I won't formally define these, but you can think of these as functioning like the 1 through n on the left. So now you have your code word, you send it through the deletion channel, you get your traces, and the synchronization string has the property that you can basically do the same alignment step, possibly with a few more erasures. So now in every trace, you've turned QN deletions into a little more than QN erasures. So now, just like on the left side, you can do this in log 1 over epsilon traces, and you can get rate 1 minus epsilon if you take your synchronization string to be over a constant size alphabet, and you take your code word symbols to be over a slightly larger constant size alphabet. So now you have, say, epsilon over 2 redundancy from the code tolerating erasures, and then you also have epsilon over 2 redundancy from the synchronization string being attached to the code word symbols. Now I'll say one word about our binary upper and lower bounds. So for our binary upper bound, we start with our large alphabet construction, and we do the standard coding theory technique of code concatenation. Unfortunately, the standard way of doing code concatenation doesn't work, and so we have to do something a little more careful. This will solve our problem. We have an exposition of this in the paper before the full proof, and so we encourage you to read the paper if you're interested. So for our binary lower bound, like for our large alphabet lower bound, we leverage Shannon's theorem. But here we have to be more careful. So we divide our code word into chunks of size square root 1 over epsilon. We treat these chunks as symbols over some large alphabet, and then we use Shannon's theorem. So then we need to compute some mutual informations, and in there we use the bounds for average case reconstruction. So I'll conclude with some open questions. First, can we close this exponential gap for worst case and average case reconstruction? Closing the gap for average case reconstruction, as we showed, we close the gap for coded trace reconstruction as well. There's also this question of practical trace reconstruction for DNA storage. So our trace reconstruction model assumed only deletions, but could you also handle insertions or duplications or substitution or other kinds of errors? Also, we assumed our deletions were IID, but could you handle non-IID deletions, which may occur in DNA? And also, as I mentioned at the beginning, our results are theoretical. The constants can be large. Can you come up with codes or algorithms for trace reconstruction when n is, say, 100 or 1,000? There was also this question asked by Wesley Pegden about necklace reconstruction or circular reconstruction. And in this setting, your traces not only have deletions, but are also randomly cyclically shifted. And you want to recover your unknown string up to a cyclic shift. Okay, so now I'll wrap up. So you saw this slide at the beginning, but now you know what all these pictures mean. So first, we motivated coded trace reconstruction by an application to DNA storage. Then I defined the problem for you formally and told you what's known about worst case and average case reconstruction. It's a difficult problem. Then I told you about our coded trace reconstruction results. So first, we do coded trace reconstruction in a constant number of traces. This is a big improvement over worst case reconstruction where we need exponentially many traces. And then I also gave our results in the context of coding for the binary deletion channel. We also showed that our results follow from a pair of black box results where we showed an equivalence between coded trace reconstruction and average case reconstruction. This says that any improvement to one is going to give you an improvement to the other, and also that our results are the best possible given our knowledge of average case reconstruction. Then I told you about our results for large alphabet trace reconstruction, that log 1 over epsilon traces is optimal, and I sketched the ideas behind the proofs. That's all. Thanks for your time.